आप लोगों को मेरी आवाज आ रही है क्लियर?
Yes, sir.
Okay ji, Bismillahirrahmanirrahim ji. I know this is a tough week for you, and this is an additional class, but we have to take this class. This is week number 7 content, which we were supposed to discuss in class number 7, but unfortunately, due to the tight scheduling, we have to take this makeup class. Okay. Now, if you remember that in the last class, we were discussing the compression members, and we finished up to this point. If you remember that, this we finished the last lecture by discussing the critical buckling stress. And if you go back to that previous lecture, so we discussed that the critical load. Where is that pen? My pen. The critical load in the columns or compression members can be estimated by using the Euler formula. And what was that Euler formula? Euler formula was given by this formulation, and this Euler formula is a function of slenderness ratio. Okay. Now, if we divide this critical load by critical if we want to have the critical stress, uh, I want to know the critical stress in your member, we have to use this formulation, and this critical stress can be estimated by this formula. Okay, this formulation. Okay, where E is the modulus of elasticity and this is the slenderness ratio. And we discussed that if we plot the critical stresses in the compression member versus the slenderness ratio, so we will get a plot like this. Okay, this was the plot. Okay, and if we see the behavior of steel structure member, you can see here in this plot you will see the critical stress versus the strain in the member. And you will see that this behavior, we already know that up to some point, let's for example in this figure, this is the proportional limit. The stresses and the strains are elastic up to the proportional limit. And if we want to project this point on this curve, so you will see this point happens to be this one. So, and one thing we should note that in this range, if we want to find out the modulus of elasticity, the modulus of the elasticity in the proportional limit or up to the proportional limit is E. And if you want to estimate the critical stresses up to the proportional limit in the compression member or in the column, so you have to use this formulation, and this formulation uses one E value only. Okay, but if you go beyond this point, or if you keep on increasing the load on your structure, what will happen that eventually you will reach this yield. Okay, and after the yield, the behavior of the structure is not linear, it becomes non-linear. Okay, and one thing you should remember that if you want to estimate the modulus of elasticity at this point, so you have to take the tangent. Okay, now this modulus of elasticity in the inelastic range will keep on changing. Okay, and the modulus of the elasticity value in the inelastic range will not be the fix. Okay, so it will keep on changing. Okay, so in this region, which is the inelastic region, if you remember, in the inelastic region you can use the same formulation, but you just have to replace the E value with the tangent modulus, and in this way you can estimate the critical stresses in the inelastic range. Okay, using this formulation you can estimate the critical stresses up to the proportional limit. Okay, so this is in this plot can be divided into two portions. Okay, the one we're having up to the elastic range. Okay, in which the material behave elastically, and the one in which the material behave inelastically. And the difference between the two is that only the E value is different in these two formulations. Okay, now this is basically, if you remember that up to the elastic buckling, so we discussed in our last class that in the cylinder columns, the stresses are in the elastic range. So up to here the stresses are elastic, and this, if you want to know, or if you want to, you are interested to calculate the critical stresses in the cylinder columns, then you have to use this formulation. And if you want to estimate the critical stresses in stocky columns or very less cylinder columns, then you have to use this formulation, because we know the failure mode of stocky columns are by yielding. Okay, and we know that the cylinder column failure is by failure in stability. Okay, आप लोगों को समझ आ रही? Is that clear to all of you?
Yes, sir.
Okay, now if you if I go back here, okay, if the Euler formula, this is if you want to estimate the critical stresses using Euler formula, if you plot that, let me grab my pen and I will change the color now. Okay, now if you plot only the Euler, this equation, this is Euler formulation for estimation of critical stresses. If you plot that critical stresses equation, so it will give you this type of behavior. Okay, this type of behavior. Okay, and actually we have this type of behavior. Okay, so this part is discarded. Okay, this part is discarded, but please remember that if you still use Euler formulation in order to estimate the critical stresses, you will not capture, or you will not be estimating the actual stresses that will be present or that will be generated in your member. Okay, so the Euler plot is this one, but this Euler plot is modified once you change the E value to tangent modulus. Then you will receive, or you will get this type of behavior. This is more of an exact behavior. This is not the realistic behavior. Okay, so if we go back to the this slide, so in this slide you will see that there is a statement that that there were some researchers that found in the Euler equation that Euler equation did not or does not give the reliable result for the stocky and cylinder columns. Okay, less cylinder columns. And why is that? Because the Euler formulation tends to follow this path. Okay, and this region after the proportional limit. So the Euler formulation is giving you this path, but actually for stocky or very less cylinder columns, this is the stress path. Okay, critical stress was versus the cylinderness part. Okay, if you use this equation to estimate the stresses in inelastic range, so you will not get the reliable result. So how did they found out? They said that if you use the same equation, Euler equation, in the inelastic range, so you will not get the reliable critical stress results. Okay, so what they did that this where is my pen? Just give me, yes, this. So this problem was solved by this scientist. Okay, this scientist in 1889. And what he did, he just replaced the elastic modulus with the tangent modulus. And then he said, now you can reliably estimate the critical stresses in the inelastic range. Okay, if you remember that in the Euler formulation, this tangent modulus is not there. Instead of tangent modulus, we have just one single value. Okay, modulus of elasticity in the linear range. Okay, if you change this Euler formulation and replace E with ET, so you can estimate up to some extent, you can say reliable, reliable stresses. Okay, stresses in the inelastic range. Okay, So now there are problems with the tangent modulus as well, okay, because the tangent modulus, if tangent modulus is less than the modulus of elasticity what you get in the elastic range, okay, this E is from here, okay, this is the tangent. If you draw tangent at any point here, so you will get the same value, this E. And if you go, if you draw tangent at this in the nonlinear range, this Et or the tangent modulus will keep on changing, okay. This is that tangent modulus, okay. So it is saying that this statement says that the tangent modulus is smaller than the modulus of elasticity we get in the linear range, okay. Now the computation is smaller than corresponds small because of the variability. And one other point is that this tangent modulus is keeps on changing at different points in the inelastic range. This is not constant. Let me write it here. Tangent modulus is not constant, okay. Let not, this is not constant, while E is constant, and this tangent modulus keeps on changing, okay. So but it is very difficult to estimate the critical stresses in the inelastic range, okay. So it is saying that this PT value, tangent modulus in the computation of critical load in the inelastic range by equation 4.5 is difficult. What is equation 4.5? This is equation 4.5, in which you have this ET value, tangent modulus, because this tangent modulus is variable. It keeps on changing, okay. So that's why, I'm sorry, that's why there is another approach which is called trial and error approach, which is used to estimate the compressive stress strain behavior in the inelastic range, okay. So that's why there are some empirical equations in the AISC specification, so that you can use to compute the critical stresses in the inelastic range, okay. So there are some as we have already discussed, that the tangent modulus in the elastic range or up to the proportional limit, the modulus of elasticity is constant, but after the this proportional limit, modulus of elasticity is not constant, okay. So in one way to estimate the critical stresses in the inelastic range was, we have already discussed that we have to replace this, or we have to introduce this tangent modulus. And if we introduce this tangent modulus in the critical stress formulation, we call this theory critical stress theory, tangent modulus theory. And we have already discussed that in the inelastic range you just have to introduce this term in the Euler formulation. This is called tangent modulus theory, okay. But there was some and we discussed that the tangent modulus theory was introduced in 1889 by this scientist, okay, because the scientist found out that Esner, okay, Esner in 1889, that the Euler theory or the Euler equation, in order to estimate the critical stresses, were not giving the reliable result in the inelastic range. So this guy proposed that you should use tangent modulus in the inelastic range, okay. And this theory we call it tangent modulus theory, and this theory had some drawbacks, okay. Now what are the drawbacks if you use tangent modulus in the inelastic range formulation of critical stresses? So what you get, you will get an underestimate of the strength of the column, because it uses the tangent modulus once the stress on the concave side exceeds the proportional limit, while the convex side is still being, okay. So this theory cannot be used for the both elastic and inelastic range, okay. This cannot be used for the both of to estimate the critical stresses both in elastic and inelastic range. And in inelastic range, what happens that it tends to underestimate the critical stresses. Okay, so this is the drawback. So what they did, people came up with another theory we called reduced modulus theory. So reduced modulus theory is another theory in which you just use this reduced modulus. And what is how we calculate this reduced modulus? Reduced modulus, okay, reduced modulus. So reduced modulus, how you can estimate reduced modulus using this formulation. Okay, so then the critical stresses, you just replace et and et value with this reduced modulus. Okay, so it also had some drawbacks. Okay, what are the drawbacks of using reduced modulus theory? That it overestimate the strength of the column. Okay, so and though otherwise it oversimplifies the inelastic buckling, so that's why it has some different, these two theories have these drawbacks. Okay, so let us come to the Euler. Is that clear to all of you? आप लोगों को समझ आ रही है?
Excuse me, sir.
Yes, sir.
चलो, अच्छा, now we will discuss the Euler Bernoulli. Oh no, sorry for the Bernoulli. Okay, Euler equation. Okay, Euler formulation.
Excuse me, sir.
Yes.
सर ये रिड्यूस मॉडुलस थ्योरी सर, ये फिर दोनों इलास्टिक और इनलास्टिक रेंज दोनों
जरा दोबारा बोले, रिड्यूस मॉडुलस थ्योरी क्या कह रहे हैं?
सर ये कह रहा हूँ कि ये फिर दोनों रेंजेस के लिए, मतलब इलास्टिक और इनलास्टिक के लिए एप्लीकेबल है।
जी 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 जी। लेकिन हम क्या करेंगे, हम इसमें जो है ये यूज करेंगे और इसमें ये यूज करेंगे।
यस सर।
ठीक है, अच्छा, अभी we will discuss the Euler formulation. Okay, in order to determine the critical load in your compression member, Euler came up with this formulation. He did not came up with this formulation. He came up with this formulation. The K term was missing in the original Euler formulation. Okay, now there were some assumption based on which the Euler formulation was derived. And what are those formulation? There are three assumptions. Okay, there are three assumptions in Euler formulation. First one is that the column is perfectly straight and it is without any initial crookedness. Crookedness का मतलब है कि आपका मेंबर बिल्कुल स्ट्रेट है जो फैक्ट्री से आया है। ओके, लेकिन हो सकता है कि इसमें थोड़ा सा ये स्ट्रेट ना हो, ये थोड़ा सा ऐसे हो। दिस इज कॉल्ड इनिशियल क्रोकेडनेस। ओके, initial crookedness. So Euler it is assumed that there is no initial crookedness in your member, and this initial crookedness will introduce bending moment. Okay, so there is no initial crookedness in your member. The load is applied concentrically. There is no, for example, you are using this wide flange section, this section as a column, and the load is applied at the centroid of this member. There is no eccentricity. Okay, and the third assumption is that was made in derivation of this Euler formulation is that the support conditions were not considered. It was considered that the compression member is pin connected. Okay, pin connected means that you have this type of support conditions, but actually you have sometimes you have a fixed support or somewhere in between fixed and hinge conditions. So in this condition the deformation or the buckling will occur in this length. So this length. Okay, now once you have changed or the support condition are changed, so you the buckling that once this buckling that will occur in this member will be changed. Okay, so in order to incorporate the support effect, we can introduce a term which is called effective length. And effective length is just a product of a k term with the length of the member. Okay, now this k term for pin connected support condition k is equal to 1. But if you have both fixed like this type of situation, then the k will be zero point 0.5. Okay, so these are the some of the assumption, but the thing is that if you want to include in the Euler formulation the support condition effect, so this formulation will stay the same. Okay, you just have to introduce this k term into this formulation. Okay, and this kl is called effective length of the member. Okay, okay. Now, this the usage of KL in place of actual length is no way alters any relation discussed so far. So if you introduce the K term in the original formulation, so if you there will be no change in the formulation. Okay, you can introduce it. Okay, so we can see that this is valid for the elastic range. This is valid for the inelastic range. Okay, now again we are discussing the those assumptions. Okay, the first one is that there is no initial crookedness. Okay, now the first two condition means that there is no bending moment in the member before the buckling. It is trying to suggest that these two assumptions which are made in Euler critical stress formulation derivation, that there is no bending moment. And the third is that the column is pinned at both ends. Okay, pin means that it can only resist the translation, the rotation it cannot resist. Okay, now please we will have this type of Euler equation is formulation is derived for this condition, but actually we may have different support conditions. Okay, we may have this support condition. Okay, or we may have this type of support condition. So the effective length or the length in which buckling will occur, or it is will be different. If the support conditions are changed, the buckling length will also change. Okay, now please remember that if he assumed that the support conditions are pinned, but constructing a pin connection is impossible. Okay, so these are just approximation, but in the field you can assume this condition or this condition. Okay, based on your knowledge. So this is all. Okay. Now what we have discussed that let me इसको मैं erase कर देता हूँ, एक सेकंड ठहर के इसको erase करता हूँ मैं। ये कल मैंने डिस्कस की थी। Okay, so what we have discussed so far is that uh, stresses, critical stresses in the columns, we have this type of there are two curves. Okay, this on the x-axis we have this slenderness ratio. Okay, if I add this k term here, so it will not change. Okay, and in this on the y-axis we have this critical stress. Okay, so if you remember that if you plot the original Euler formulation, so it's a con, convex or concave. Is it convex or concave? Okay, so let me grab another pen here. Where is this one? इसको इसको हम अगर ग्रीन कर दें यहाँ पे, so up to the proportional limit, the behavior or the plot between the critical stress and slenderness ratio is different. So you cannot use Euler formulation in order to estimate the critical stresses in the inelastic range. Okay. So what we have discussed, that this is the proportional limit. Okay. So there is a division between elastic and inelastic region. Okay, so this is representing the elastic region and this is representing the inelastic region. And elastic means that we know that the cylinder columns, cylinder columns, we have elastic stresses. Okay, and in the inelastic, we in the stocky or less cylinder column, less cylinder column, we have inelastic stresses. Okay, in this we can estimate the critical stress using the original Euler equation, which is I think E pi, this one, KL by R square. And in this you can use this modified version. This is ET pi square divided by KL over R square. Okay, please remember that. Okay, so we will see that the borderline between elastic and inelastic region can be approximated. I think if you have the AISC code suggests that Fy by E, I think, or E by Fy, I think this is E by Fy. This point is 4.71. Okay, simply you can know that if you calculate for your member this ratio, if it is greater than this one, so it means that the member is cylinder, and if it is less than this one, this value, so member will be stocky. Okay, so now let's go to the AISC requirement. And we know that we have two approaches for which we can go for the with which we can go for the design and analysis of the structure. The first approach is LRFT. Okay, now LRFT suggests that the nominal compressive strength of an axial or the compression member or column can be estimated using this formulation. Okay, now you can see that critical stresses are required. Okay, critical stresses are required to calculate, to compute the capacity. Okay, once you know the critical stresses. Okay, but the critical stresses are two, like there are criticals, there are different formulation of critical stresses in the elastic range. Okay, the formulation is different, and if the critical stresses are in elastic range, you have to use a different formulation. Okay, so critical stresses are required and you need the gross cross-sectional area. If you multiply the critical stresses with the gross cross-sectional area, so you will get the nominal compressive strength of the member. And if you multiply this with the phi c value, so you will get the design compressive strength of the member. And this phi c value in the LRFD takes a value of 0.9. Okay, and this design capacity should be less than the demand. Okay, based on LRFT approach. Now similar to the LRFT approach, we have a second approach we call allowable stress design or allowable strength design. So this requires that the allowable strength or the allowable compressive strength should be less than the demand. Okay, or at least equal. No, sorry, this allowable compressive strength should be greater or at least equal to the demand. And the factor of safety in order to evaluate the compressive strength of the axial members or columns happens to be 1.67. Okay, if you want to use the allowable stress formulation, Now, allowable stress formulation, you need to use this formulation. And if you want to go with this approach, so just you have to compute the uh, critical stresses and you have to divide it by 1.67. And if you solve this, so you will get a value of this one, that compressive stresses or the stresses in the compressive member should be less than, okay, or equal to this magnitude of stress. Okay, so mostly we will follow this one, this formulation, okay, in this lecture. So now we know that in order the Euler load or we can estimate using this formulation. Okay, and Euler stress, we divide this by the cross sectional area of our member, so we will get this formulation. This is the critical stress or the Euler stress, we can say, but it is generalized here. It is saying it's an Euler stress, but we know that we can divide E, we can replace E with tangent modulus. Okay, so this is critical stress or this is critical load. Okay, but we know that in the derivation of this equation there are certain assumptions. Okay, so if the AISC requires has modified this equation, this original equation, it requires that you should reduce the critical stress or the Euler stress in your member. Okay, for elastic region, in the critical stress versus the slenderness plot, you should use this equation instead of this equation. And in the inelastic region, you should use this equation. Okay, not, you don't have to use this ET and EAC, reduce um, elastic modulus or tangent modulus, forget about it. You just use this empirical equation. Okay, empirical equation. Okay, what is with the slight modification, the expression for the critic in the elastic region. Okay, you can read out this because due to the Euler assumption, initial crookedness. Okay, so you can reduce the critical stress magnitude what you get from the Euler formulation. Okay, so this equation we will use in our design. So as I told you that the critical stresses and the slenderness plot has been divided into two portions, elastic portion and inelastic portion. Okay. First, in order to see that what type of behavior is expected in your member, you have to calculate this ratio first. First, you have to calculate this one, and then you have to go to the plot. You remember this plot, okay? This is KL by R. Okay, you have to see that what is the value of KL by R, and this bordering point, as I told you, that this take AISC suggests that it takes a value of this one. Okay, this is the value. So you have to compare it. If the KL by R value is less than or equal to this value, it means that you are in the inelastic range. And you should use this empirical equation. Okay. And if KL over R is greater than this point, so it means that you are in this region, elastic region. Then you will use this equation. Okay. Now the complete formulation is that the same thing is repeated here. Okay, so this equation can be simplified by just calculating the Fy by Fe value. Okay, if you cannot remember all of this, so just you can calculate the material Fy divided by the effective or the critical stresses. And this critical stresses, I think Fy is somewhere, this is uh, you can use this Euler formulation if I remember correctly. Yes, KL by R square. So we will see how we can estimate Fe value. So This is again the same thing. Okay, now this AI, as I told you that up to the proportional limit there is a borderline after the proportional limit. So this curve can be divided into two parts. Okay, in this part you can use this formulation, and in the inelastic part you will use this formulation. So these are the empirical equation. Okay, the empirical equations are being used. Okay, so one thing, remember that this is about the global stability or global failure. This is global, representing the global failure. But as I told you that in the steel structure we also have local failures. Okay, and this local failure can also occur in the compression members. Okay, look, what is that local failure we call, this local failure, for example, you have a column here, let me write here, and if you apply a load and the cross section is this one, this is a wide flange section, and there is a possibility that this can buckle and you have failure of this member. Okay, this is a global failure. Okay, or the failure in the flexure you can say. Okay, because flexure represents the uh, global failure mode of the compression member for the cylinder compression member of our cylinder columns. Okay, but there is a possibility that this part of the member can also buckle, this can fail also, local fail, local failure. Okay, this is local failure. And what is meant by local failure and what causes this local failure? Local, it can fail in localized stability in torsion, and it can fail in the flexure, or it can fail in combination and flexure of and torsion, or it can fail in combination of torsion and flexure. Okay, so localized failure is also, we have to check for the local failure as well. Okay, now this is all about the global failure. We are checking for the global failure, but how we can check for the local failure or local stability failure? So we have to go through some literature first, but first we will discuss the global failure or the flexure failure, flexure or the global failure, global failure. Okay, now you can see that there is a white flange section. Okay, now the material type is A992 steel, and the length of this member is 20 feet. And in the statement you can see that the pinned end condition is also, support condition is given, and you are supposed to calculate the compressive strength of this member based on LRFT and ASD approaches. And if you remember that the nominal strength is a function of, is a function of critical stress. You need to calculate the critical stress and you need to know the gross cross sectional area. The gross cross sectional area you can simply find it from this AISC manual. And the critical stress, you need to estimate critical stress. Okay, but in order to estimate the critical stress we have two type of formulation. For that we have to check this limit. First you need to calculate this ratio, slenderness ratio. Okay, now slenderness ratio, you have to calculate the K value for the pin ended condition is 1. Okay, so as I told you that we have to check for that, in we discussed in the last lecture that the L by R ratio, and now it is KL by R ratio for compression member should be less than 200 in order to avoid this slenderness check or stability failure. Okay, so this is the requirement of AISC in stability for, sorry, for stability check. So you have to check it first. Is it to less than 200? So fine. What next? You have to calculate the border point, bordering line or border point between elastic and inelastic region. If this value is greater, if you are getting a greater value than this value, then you will be in the elastic range. So you will use this formulation. I think this is 0.877 FE. Okay, if this value is greater than this one, but since the value is less than this one, so we are in the inelastic range. And in order to estimate the critical stresses in the inelastic range, we have the AISC suggests to use this equation. Okay, and in order to compute this equation, or in order to use this equation, we need a value of FE. And FE value you can calculate with this formulation. Then this FE value you can just plug in this value in this equation, and you will get the critical stress value, which comes out to be uh, 25.21 kips. This one. And this is FY for A double 92 steel. Okay. Now, once you know the nominal capacity, okay, let me check. Are we connected? Can you hear me?
Yes, sir.
ओके।
Yes, sir.
चलिए, नींद आ रही है आप लोगों को, लेकिन क्या कर सकते हैं, हमारी नींद भी खराब हुई है, क्या करें। ओके, now you can calculate the nominal capacity. Okay, this is nominal capacity. You have nominal capacity, compression capacity, or compression strength, let's say. So if you multiply it with phi value, so you will get the design compression strength. P value is 0.9. Now for ASD, we know that we discussed that you can use the stress formulation. You have critical stresses. Now you multiply it 0.6. So this is the allowable stresses. Okay. Now similarly, you have to multiply this allowable stresses with the gross cross-sectional area. So you will get the compression strength based on ASD. Okay. This is compression strength based on LRFD. This is the strength of this member, capacity of this member. Okay. This is based on ASD. This is based on LRFD. Okay. Now, as I told you that we also have to check for the local stability. Okay. Local stability failure occurs in the cross section. Okay. And if you have this type of failure, then the capacity of your member, or the global capacity of your member, will be reduced. Okay. So if we go through this statement, the strength corresponding to any buckling mode cannot be developed if the elements of the cross sections are so thin that the local buckling occurs. This type of instability is called localized buckling or wrinkling at an isolated, and it happens or it occurs at isolated location. If it occurs, the cross section is no longer fully effective, and the member is said to be or assumed to be failed. Okay, before developing the full global capacity, it can fail in local stability if the uh, components of the cross sections are very thin. Okay, in I and H shaped cross sections with thin flanges or webs are susceptible to this phenomena, and their use should be avoided whenever possible. Okay, otherwise compressive strength given by this must be reduced. You are not supposed to use the cross section in which they are the cross sections which are susceptible to the localized buckling. If still you want to use it, then you have to reduce your global capacity. Okay, now how do we measure this capacity or local susceptibility? We just take the ratio of width to thickness of these cross sections. Okay, now, and we will see in a moment how we can do that. So there are two type of elements in any cross section. We call unstiffened elements and stiffened elements. What are stiffened elements? Stiffened elements are those elements of the cross section which are supported at both ends. Okay, both ends. So this is a stiffened element. And the members which are supported at one point and they are free at other point, other location, or other end, we call it unstiffened. Unstiffened. Unstiffened elements. Okay, so basically there is two, stiffened and unstiffened. Okay, so limiting values, okay, let me इसको मैं हटा दूं. Okay, आगे भी है. Okay, we were here somewhere. Okay, now limiting value of width to thickness ratios are given in AISC before. Okay, okay, classification in this, they can be classified as just give me a moment. They can be classified as compact. The cross sectional shapes can be classified as compact, non-compact, or cylinder sections. Okay, no, and this is based on the thickness, width to thickness ratios. Okay, now this division of in AISC is based on width to thickness ratio. Okay, this ratio. For uniformly compressed element, okay, we have already selected the strength must be reduced if the shape is cylinder. Okay, okay. Now this is that how we can check the localized stability. Okay, now for example, you have to calculate this lambda value, and this lambda value is a ratio between the width and the thickness, and this is for the case of this wide flange section. Wide flange section, this is B. Okay, and thickness is T. So what you have to do is you have to take the ratio of this two. Okay, and in this case B is this one. This is unstiffened element. B is BF by, sorry, BF by 2. Okay, now this is lambda. Okay, now you have to compare this value with the code given value, which is this one. If your value is less than this one, so your cross section will be not cylinder. Okay, if this is for the flange, for webs you have to follow this formulation. This is called H and thickness of web, this one, and you calculate this and you compare it with this lambda r value. If your value is less than this one, oh sorry, if this is greater than the ratio what you are getting from this formulation or this formulation, so your member will be not cylinder. Okay, so there will be no localized buckling in the member. Okay, so in order to demonstrate it, so you can see that there are two limiting values or two equations which are set by this AISC. Okay, now well, you have to calculate the width to thickness ratio and you have to compare it. This is for flange. If you are doing it for flange, so you can use this equation, and if you are doing it for the web, so you can use this equation. So thickness ratio should be compared with this. If you are evaluating the, or you are just checking the susceptibility of your cross section, and if you are using it for the you are checking the flanges, so you have to compare it with this one. So different equations are given here. Okay, so you can see this is for wide flange section, this is for T, this is for structural T, I think, or wide flange T or miscellaneous T. This is for channels with, this is for double angle. Okay, this is for double angle without gusset plate. So this is for built up sections. Okay, now this you have to compare it. Okay, there are some certain values which are given in AISC table. Okay, so you have to compare, you have to use this equation to check the local stability. And in order to demonstrate it, so we will go through an example, that is example 4.3. In example 4.3 there is a section. Let me इसको मैं erase करूं, ये फिर आ गया. This one, this I should delete it. And it should I say that. Okay. बहुत सिंपल है, कोई इसमें कोई बहुत बड़ी साइंस नहीं है. ओके, नाउ इन्वेस्टिगेट द कॉलम लोकल स्टेबिलिटी. ओके, so the section is given. What is that section? Okay, cross section is given, this cross section. Okay, this cross section is given, and this cross section is shown here. Okay, now first you have to check the ratio of the widths for flanges. Okay, this is flange. Okay, this is flange, इस पोर्शन की बात कर रहे हैं, ठीक है. तो टोटल फ्लैंज क्या है? दिस इज बी एफ. बी एफ इज एक्चुअली दिस वन. BF, you should divide it by thickness. This thickness is TF. So you will calculate and you will get a number. Now for flanges, according to, this is the lambda equation. This is according to AISC recommendation. So you will compute this ratio. Okay. Now this ratio is 13.5, which is greater than this value. So there will be no local stability issue in the flanges of your member. Okay. This is given here. Okay. Now we will check the webs. Okay, the webs are like, you have to subtract D is from here. I think D is the total depth. This is the total depth. Now you have to subtract mine 2 times this factor. Okay, what is this factor? Actually, if you look at this white flange section, so over here this is like this. So this is, there is a curvature here. So this is that curvature. Okay, so this H is from here to here, straight portion. Now where DES is the design value of K, different manufacturer. Okay, so who will give you this value? The manufacturer of sections. Okay, so you can calculate this and then you can compare it with this equation. So this equation is empirical equation, is giving you this value, and your thick web to height to thickness ratio is giving you this. So there are both of you. Okay, it means that there will be no stability issue in your member. Okay. Okay, I will come back to the class now. Where are we now? What is happening? समझ आ रही है आपको कुछ?
यस सर.
अच्छा, चलें एक 5 मिनट का ब्रेक लेते हैं, ठीक है, फिर शुरू करते हैं. सही है. इन द मीन वाइल आप लोग सोचें कि अगर आपका कोई क्वेश्चन हो तो आप पूछ सकते हैं. ठीक है.
सर वो पीछे एग्जाम्पल में FE की समझ नहीं है.
अच्छा, FE आप मुझे बताते जाएं. ठीक है. FE इसकी, इस FE की.
सर सर आई थिंक इसके इसके पीछे जो एग्जांपल है या सर इसके इसके बाद जो है सर
एक सेकेंड, आगे क्यों नहीं जा रही है? हाँ, ये वाली है, ये सबर करें में, इसके बाद तो सबर करें,
सर आई थिंक इज 4.2
4.2। अच्छा जी, एफ ई वैल्यू की कहाँ समझ नहीं आई आपको?
सर ये एफ ई वैल्यू हम एफ ई किस तरह इसमें फर्क क्या है सर
देखें,
ये क्रिटिकल और एफ ई में
देखें ये तो ये है ना, क्रिटिकल, एक्चुअली दिस इज क्रिटिकल। ठीक है, मैं आपको बताता हूँ, एक सेकंड, ये इसको मैं पेन ले लूँ यहाँ से, ठीक है। एक तो देखिए, क्रिटिकल स्ट्रेसेस आर लाइक एस्टिमेटेड बाय आइलर। आइलर की जो इक्वेशन है ना, वो ये मैं इधर लिखता हूँ, देखें हमने क्या पढ़ा है कि दिस पी सी आर इज इक्वल टू क्रिटिकल लोड इज इक्वल टू पाई ई ए बाय, ये इक्वेशन थी ना, ठीक है। अब इसको हम जब ए पे डिवाइड करते हैं, इफ आई यूज दिस फॉर्मुलेशन, ठीक है, तो दिस विल गेट कैंसल आउट एंड वी विल बी लेफ्ट विद दिस इक्वेशन, पाई ई एल बाई आर, ठीक है। ये इक्वेशन और ये इक्वेशन ऑलमोस्ट सेम है, ठीक है ना, सॉरी इसमें पाई स्क्वायर, आई एम सॉरी, सिमिलर है ना, इन दोनों में कोई फर्क है? फर्क है?
नो सर ये सही है
नहीं, फर्क है ना, दिस के टाइम्स
नो
पाई,
सर
इसमें के नहीं है। तो if you add k, because this equation is based on assumption that the support conditions are pinned, ऐसा ही है ना, support conditions are pinned, it means that L is equal to original length, मतलब k is equal to 1, k फैक्टर को कंसीडर नहीं करते। तो कोड क्या कहता है कि उसने उसको मॉडिफाई किया है और यहाँ पे उसने k इंट्रोड्यूस कर दिया है, तो इन दोनों में सिर्फ ये फर्क है। अभी क्लियर हुआ कुछ?
सर तो इसके बाद फिर हम ये एफ ई के बाद एफ क्रिटिकल दोबारा क्यों मालूम करते हैं सर
अच्छा ठीक, एक सेकंड, अच्छा एक सेकंड, दो किस्म की क्रिटिकल स्ट्रेस की फॉर्मुलेशंस हैं, ठीक है। आपको बैकग्राउंड में आवाज तो बहुत ज्यादा नहीं आ रही?
नो सर सही है
ये देखें, एक क्रिटिकल स्ट्रेस की ये फॉर्मुलेशन है, ठीक है, और एक क्रिटिकल स्ट्रेस की ये फॉर्मुलेशन है। इन दोनों के दरमियान क्या फर्क है? दिस इज वैलिड इन दिस रीजन, और ये रीजन मैं इस तरह करता हूँ, ये देखें, ये रीजन, दिस इज वैलिड इन दिस रीजन, और दिस इक्वेशन इज वैलिड इन, अच्छा अभी आपको क्या पता है कि ये रीजन में डिफरेंस क्या है? तो देर इज अ बॉर्डरिंग लाइन, ये बॉर्डर है इन दोनों के दरमियान, और उस बॉर्डर की क्या वैल्यू है? ये वैल्यू है। और एक्स एक्सिस पे क्या चीज है? के एल बाई आर। आपने क्या करना है? के एल बाई आर कैलकुलेट करना है, और देन यू हैव टू कंपेयर इट विद दिस इक्वेशन। अगर के एल बाई आर की वैल्यू इससे ग्रेटर है इस इक्वेशन से, तो आप इस रेंज में, इलास्टिक रेंज में, तो उसके लिए आप कौन सी इक्वेशन यूज करेंगे? ये। अगर इफ के एल बाई आर इज लेस देन दिस इक्वेशन, तो देन इस रीजन में आप होंगे। तो इस रीजन में कौन सी इक्वेशन यूज करेंगे? ये वाली। इसमें आपको एफ वाई चाहिए, इसमें आपको एफ ई चाहिए। एफ ई की वैल्यू कैसे एस्टिमेट करेंगे, वो अभी हम वो एग्जांपल में जो देख रहे थे। कुछ समझ आया आपको?
सर समझ आ गया।
अच्छा, तो सबसे पहला काम अगर आप इस एग्जांपल में देखें तो पहला काम आपने क्या कर किया? के एल और बाई आर निकाला, ठीक है। उसकी वैल्यू क्या है? 97। सिलेंडरनेस रेशियो के चेक के लिए इट शुड बी लेस देन 200। टेंशन मेंबर में इट शुड बी 300 से कम होना चाहिए, लेकिन इसको छोड़ें, ये वैल्यू आ गई 200 से कम है, फाइन। अगला काम क्या किया हमने? वो बॉर्डरिंग पॉइंट, ये वाला पॉइंट जो है, ये वाला, ये कैलकुलेट किया, ठीक है। इसमें कौन सा मटेरियल हम यूज कर रहे हैं? दिस वन। इसकी एफ वाई वैल्यू क्या है? 50। यस, ये वैल्यू यहां पे प्लग की तो वी गेट अ नंबर 113। 113 जो है हमारे पास, ये पॉइंट जो है, लोडिंग इसने शुरू कर दी, एक सेकेंड। हाँ, ये पॉइंट कितना है? 113। और के एल और आर की वैल्यू क्या है? 96। वो इस जगह पे। कौन सी इक्वेशन यूज करेंगे इन ऑर्डर टू एस्टिमेट द क्रिटिकल स्ट्रेसेस? ये वाली कि ये वाली?
सर लेफ्ट वाली।
ये वाली करेंगे, ये वाली, बिकॉज दिस इज वैलिड इन दिस रेंज। तो अगर आप उस एग्जांपल में जाएं तो वो ये इक्वेशन यूज कर रहे हैं, और उस इक्वेशन में इट इज अ फंक्शन ऑफ एफ ई, और एफ ई की वैल्यू उसने पहले कैलकुलेट की। उस एफ ई को यूज करते हुए उसका
सर
जी,
सर बेसिकली एफ ई और एफ क्रिटिकल में फर्क क्या है सर, एफ सी आर और एफ ई में?
अच्छा, ये फर्क है। ओरिजिनल इक्वेशन क्या है देखें, ये है, दिस इज एफ ई, ठीक है। ये एफ ई है, देखिए मैं यहां लिखता हूं, देखें एफ ई इज इक्वल टू पाई स्क्वेयर ई के एल बाई आर। दिस इज एफ ई, ठीक है। अच्छा, ये इक्वेशन जब डिराइव की गई तो देयर वर सम सर्टन इजम्पशंस। वो इजम्पशंस क्या क्या थी? ये कॉलम इज परफेक्टली स्ट्रेट with no initial crookedness. The load is axial. The column is spin at both ends. ये तो हमने के से कर लिया इसको। इन दोनों को करने के लिए उन्होंने क्या किया? कोर्ट कहता है कि ये कहता है कि जो मेंबर होते हैं, फर्ज करें ये क्रॉस सेक्शन है, एक ये वाला ना, ये वाला, दिस इज वाइड फ्रेंच सेक्शन। और अगर इसको हम प्लेस करें तो बिल्कुल स्ट्रेट होना चाहिए, बिल्कुल, सॉरी मेरी ड्राइंग में जरा इसको फिर, बिल्कुल स्ट्रेट होना चाहिए। इसको छोड़ें, इधर बनाता हूं, बिल्कुल स्ट्रेट होना चाहिए। क्या ये बिल्कुल स्ट्रेट है? ये मेंबर बिल्कुल स्ट्रेट है कि नहीं है?
यस
नहीं
सर।
है, नहीं है। इस चीज को क्या कहते हैं? क्रोकेडनेस, क्रोकेडनेस। और ये कौन कैसे इंट्रोड्यूस होती है? जब मेंबर आप कास्ट करके फैक्ट्री से आते हैं तो वो बिल्कुल स्ट्रेट नहीं होते, उनमें ये इनिशियल क्रोकेडनेस होती है। So that's why is in order to take care into this account, this factor, कोर्ट क्या कहता है कि आप इस इक्वेशन को इस्तेमाल मत करें, आप इसको थोड़ा सा रिड्यूस कर लें, इसको वो AISC इसको क्रिटिकल स्ट्रेस इंपेरिकल इक्वेशन कहती है। ठीक है, ये देखें, अगर with slight modification this expression will be used for critical stresses in the elastic region. To obtain the critical stress for elastic column, the Euler stress equation is reduced as to account for effects of initial crookedness. अगर कोर्ट की बात
Yes,
न
sir, I get it.
हाँ, अगर कोर्ट की बात ना करें तो ये क्रिटिकल स्ट्रेस इक्वेशन यही है, लेकिन AISC कहते हैं कि आप इसको थोड़ा सा रिड्यूस कर लें। अभी समझ आई है?
Yes, sir, I will use. Thank you, sir.
चलो इस तरह करते हैं, क्या टाइम है अभी, 5 मिनट का ब्रेक ले लें। चाय पीनी है आप लोगों ने कि नहीं?
Yes, sir.
तो कितना ब्रेक ले लें?
सर 30 मिनट ब्रेक दे।
ठीक है, लेकिन वापस आना है ना, आई ना फिर क्या करेंगे? अच्छा, तो मैं रिकॉर्डिंग स्टॉप कर रहा हूँ और फिर हम 20 मिनट बाद आते हैं जी। ठीक है।